Welcome to this short lecture on gravitational waves, where we explore how ripples in spacetime reveal the universe in a brand new way. Over the next slides, we'll unpack the 2015 discovery, the instruments that made it possible, and the scientific breakthroughs that followed, using clear visuals and analogies to make complex ideas easy to follow. The 2015 detection transformed astrophysics by opening a new observational window. It inaugurated gravitational wave astronomy, provided direct tests of general relativity under extreme conditions, offered a new method for measuring cosmic expansion, and let us probe matter at neutron star densities, all of which the diagram links together as complementary advances in our understanding. Einstein taught us to think of gravity as geometry, not a force, and this slide's illustrations show spacetime like a stretched sheet bowed by mass. When massive objects accelerate asymmetrically, they perturb that geometry, launching outward ripples, gravitational waves, a bit like shaking a bedsheet and watching waves travel across its surface. Before direct detection, clever indirect evidence paved the way. The binary pulsar PSR B1000 913 plus 16 showed orbital decay matching gravitational wave energy loss, earning a Nobel Prize and motivating the development of ultra-sensitive detectors like LIGO and Virgo, as the timeline and diagrams on this slide explain. Gravitational waves arise whenever mass accelerates unevenly, but the loudest signals come from compact binaries. The left diagram shows asymmetric acceleration, creating ripples, while the right illustrates two compact objects spiraling inward, with frequency and amplitude rising dramatically during the inspiral until the eventual merger. Beyond mergers, many astrophysical processes imprint distinct waveforms we can use as probes. As illustrated here, asymmetric supernovae produce short bursts, deformed spinning neutron stars give continuous tones, cosmic strings could create cusp-like events, and early universe phase transitions yield stochastic backgrounds, each carrying diagnostic frequency signatures. Ground-based observatories like LIGO and Virgo use laser interferometry to sense minuscule length changes as gravitational waves pass. The schematic shows perpendicular arms, a beam splitter, and mirrors producing interference fringes. Sophisticated isolation and multi-site validation suppress seismic and thermal noise, so genuine cosmic signals can be confirmed. Looking to lower frequencies, space-based detectors and pulsar timing arrays open new windows. LISA will use million-kilometer laser arms to track supermassive black hole signals, while pulsar timing monitors millisecond pulsars across the galaxy to detect nanohertz stochastic backgrounds from merging supermassive binaries, offering complementary sensitivity to very large-scale processes. Gravitational wave observations let us test general relativity in its strongest regimes. The precise ring-down waveforms seen after black hole mergers confirm the no-hair theorem and allow accurate spin measurements, while careful searches for deviations probe alternative theories, so far strengthening confidence in Einstein's predictions under extreme gravity. Merging binaries act as standard sirens because their waveforms encode intrinsic luminosity and yield direct distance measurements without a cosmic ladder. Combining that distance with redshift provides independent Hubble constant estimates and maps of cosmic expansion history, offering a powerful route to resolve current cosmological tensions. The future of gravitational wave astronomy aims for much greater sensitivity and entirely new frontiers. Planned ground upgrades and third-generation detectors will multiply reach. Space missions like LISA will trace supermassive black hole growth, and searches for primordial backgrounds promise to open unexplored epochs from the early universe. Multi-messenger astronomy combines gravitational waves with electromagnetic and neutrino signals to give holistic views of extreme events. By merging these channels, we learn merger environments, the origins of heavy elements through kilonovae, and jet formation mechanics, building comprehensive cosmic narratives, and unlocking discoveries across fundamental physics.